So today I'm going to talk to you about improvements to the UK MTHS25 method for the determination of diisocyanates by adding gradient chromatography. So that's the lab for those of you who don't know. There's lots of people here from HPLC. That's our main laboratory here at Buxton, which is nearby, relatively nearby. So, first of all, give you some background on what isocyanates are. So, the monoisocyanates are industrial chemical precursors. I'll come back to monoisocyanates as we talk. This is primarily about diisocyanates. So, a very common ingredient in formulations for things like foams. They're usually manufactured foams. So, you're all sitting on an isocyanate foam. They have them in here. And then adhesives, so that's more, when they're using foams, they're reactive, so it's only in the manufacture that you might be exposed, but in adhesives and paints, in the use of them, they're still there as the reactive ingredients, so they get exposed in use as well as manufacture. So there are many different structures, but they all contain this NC double bond group, and that's the active site for the health risk. And so this is an example molecule. You can see the three different isomers of this one molecular type. This is methylene diphenyl diisocyanate. That's the one that you use in adhesives mainly, also in foams, also in paints. There, so you've got three different isomers there, and then these can join together. And then in use, you often use short-chain polymers. That changes the property of the material in use and also reduces the volatility, so it's a little bit safer depending on how you're using them. If you're aerosolizing the volatility, it doesn't really make any difference to the health risk. So, why are we concerned about isocyanates? So they're potent respiratory sensitizers, and very low levels in exposures, very low levels can result in severe asthma. So, and they're one of the most common causes of occupational asthma, certainly in the UK. I've just been examining their data, and that's still the case. So, workplace exposure limit is very low, 0.02 milligrams per cubic metre, so that's less than silica that Chris was talking about earlier, similar to mercury. But unusually, the workplace exposure limit is for all isocyanates. We've just described how many different molecular species you might be looking for, and you've got to measure them all. But you've got to separate them all to measure them. It's not like a metal that you can just reduce it down to the single component and measure that. You've got to measure all the actual molecular species. And you measure those as total reactive isocyanate groups, and that's the agreed metric for the health risk from things like the European Chemical Agency. So, current position in MTHS25 is the sample is used in a derivatization reaction with 1,2-methoxypyrazine, and then measure that with isochromatic HPLC. So that's the continuous mobile phase, same composition, which is pumped through a column. It's a phosphate buffer with acetonitrile, and use a dual detector technique, and the ratio of responses from the two detectors verifies the type of isocyanate. So you can quantify based on the response from one monomer, and use that to measure the polymers of that species in the same response. So you don't need to calibrate for everything. You can calibrate for all these other peaks. You can calibrate just using this peak for these ones. As long as it's the same base monomer, you get a different response from the different base monomers. But there are long run times, poor resolution for the monomers from the reagent peak. So you can see here, this is the reagent peak, 1,2-methoxypyrazine. These are your monomers coming off. So this is very highly tailored, and there's a lot of it. And then it's also sensitive to small changes in the mobile phase composition. So when you make it up, you have to get it spot on, or this peak disappears here into the reagent peak, and you don't get the calibration you have to start again. And as you can see, these peaks on very I don't know if any of you saw Goswell's presentation this morning with his nice sharp GCMS peaks. they're not, you don't often get those in HPLC, or you often don't get them in HPLC, especially isostatic HPLC. But gradient wasn't possible earlier on because the system just blocked when you tried it, so it wasn't very helpful. And also, if you run gradients, I'll come on to another reason, it's about background signal. So moving on, why do we want to change? Well, we got a nice shiny new instrument, and we use an instrument for a lot of different HPLC methods, but through that use we realised that pump performance was much improved and the detector stability from the instrument was excellent. And also you have software tools, and you use software, and that allows you to subtract the background from the background. So this is a very different tool. So in general, why would we want to go to gradient methods where you get improved resolution, great sensitivity, and ideally normally shorter analysis times? Analysis time is a very complex parameter, so yeah, that's good. So initial charge. So first of all, I need to check that it's safe to do this. So on this gradient, I don't want to destroy my detector by blocking it, which we do a lot in the development of the isocratic method. Installing the isocratic method on this instrument, so transferring the method from the old instrument to this new instrument in cooperation with the instrument manufacturer, we actually broke a lot of detectors. So we learned a lot about how to compare the mobile phase. So first of all, check the back pressure stability. So I ran a small gradient. Now, as I explained, we learned a lot about the mobile phase preparation. So preparation of the mobile phase is a mixture of a phosphate buffer and acetonitrile. Now, you have to be very careful in the mixing of that, otherwise you get precipitation in the mobile phase, very tiny. It's not an obvious crashing out, precipitation in the mobile phase. And those tiny crystals block the porous electrode detector with the electrical input detector. So if we're very careful in the mixing, because of that, when we're doing the mixing, normally when you do a gradient, you'll have your buffer in one vessel, and your solvent in the other vessel, and you mix them in the pump, and away you go. If you did that, you wouldn't get good results with this. So I started with two pre-mixed buffers, only 10% different, 50% buffer and 40% buffer. There's no detector to check the detector back pressure. Mix them online, and then we got a 10 bar change in gradient. That's very consistent. So no spikes indicating problems during the run, I think. So the next step was detector stability. Do you get good repeatability in the detector so that you can, as you can imagine, if you use this method, these are the two different stages. If you had this and run it, you had peaks overlaid on this, your integration would be very difficult. So that's why we're using grammatical subtraction to take that away. That's the software tool. So in order to actually work through the run, it has to be consistent. So this is overlaying injections of the detector, 3 consecutive injections, very consistent detector background signal. There's no injection here, this is just mock injection. So the injections didn't run, but everything else about the run worked. So you get good consistency. Excellent. Moving on to the next step. So then I try out different gradients. So this isn't right, I'm sorry, there's a lot of data on this slide in order to read this all, but just to say that this is the first gradient, 40%, 50% buffer. I expanded that out to 30% buffer, going out to 60% buffer, and in stepwise things, so 5 minutes, 10 minutes. The peak shape vastly improved. This is the latest elution HDI, that's hexamethylene diisocyanate. That's a linear chain of 6 carbons with isocyanate group on either end. And you get this peak is normalised for peak height, as well saying, but it's the same injection size, normalised for peak height, just to show the improvement in peak width at half height. So peak width at half height is a quarter of what it was with the isocratic method. So this is superb performance. So and move on further investigation. So I mentioned monoisocyanates earlier. So monoisocyanates, things like the classic is the diisocyanates in this case, our main interest is in decomposition products. So these were foundry, so foundries in high temperatures, and they use methylene diphenyl diisocyanate to bind the sand together when they're doing moulding of the foundry. Then they pour them over methylene, and that MDI is heated to high temperatures and decomposes, and it makes monoisocyanate. So normally these can't be analysed by the isocratic method. They could be analysed by the gradient method. Good separation, and look, nice sharp peaks. And I've really subtracted away that ugly reagent peak, which improves sensitivity for the later limited peaks. So, good resolution of monomers and oligomers when you're able to peak, slight shorter runtime, and more resolution. So this is HDI that was inside the reagent peak up here before, and that's eluting much later, and it's resolved from these two. So this is something you couldn't do with the isocratic method, which you can now do with the gradient method. Then I tried it on real samples, just because I had some from a customer. So real samples are always different to mock samples if you don't. Analysed it, and this is the isocratic chase thing, and you can see there's an unknown here in the samples. This is the standard. It's well resolved in the isocratic method. But in the gradient method, the 95 gradient, the co-elutor decided to go back to the drawing board. And now I knew something about this, so I knew that the isocratic method you get resolution, you didn't get it. So a higher solvent concentration in the mobile phase at the starting run will give you separation of the unknown, this unknown from the HDI. So then I try instead of 95% of the 60% buffer starting material, I started with 80%, and then I get resolution from HDI. So just to go through how serious a problem this unknown was, this is the unknown from the real sample, and I've added, this is HDI in the real sample. I've added the standard of HDI. And you can see these are on the same scale. They're overlaid scale. So you can see the relative height of the peak. This is 50% of the calibration range. So the unknown is very significant level of chemical contamination. So we retain new 80 to 5 gradient, retains good resolution of the monomers, so they're all the way out here, PDI, MDI, and then these different oligomers. Good sensitivity, improved sensitivity, and you've got resolution up here, and it's well away from the reagent peak, which is well separated from us. And you've nicely corrected for that change in the baseline. So, moving on to final validation. So I wanted a range of isocyanate bulks. It's a lot easier to get these from version of isocyanates to test from, and you need to prove that you're recovering isocyanate by your method. So by analysing bulk material isocyanates, bulk products that are in use, you can calculate, you can find by titration the total isocyanate in the sample, and then you can check whether your method is recovering all that isocyanate from the bulk. i.e., does everything add up? When you put all these peaks together, does it add up to the titration result? And for HDI, it was quantitatively recovered from the bulk, results match the titration rates. MDI oligomers did not match the titration results, but they were consistent with the high isocratic method. We were also analysed by the dibutylamine method, which is a different derivatizing reagent, and measurement by mass spectrometry. And the three different MDI bulks were analysed in triplicate for by titration, dibutylamine, isocratic and gradient, and recoveries were consistent between all three HPLC results, the mean 91%, 130%, mean 110%. Reasonable relative standard deviation between dimethylamine and MDI. So, although you can't recover everything from the titration, all your methods are consistent. So the reason you can't recover is some of these MDI oligomers here. These are they're rather large, 5-ring. They just don't come off the column. So, moving on. Overall, gradient improves the calibration. I haven't shown the calibration quickly, but you get a lot better sensitivity and also better fit to the calibration line. As I said, sensitivity is improved, especially for HDI because it's separated from the 120 reagent peak, and then the later releasing the ligament because peak shape is vastly improved. Response ratio, I haven't talked about response ratio very much, but I mentioned relative response to the detector. That allows you to find the result, to identify the peak of an anisocyanate. Now, ideally, the monomer and the oligomer should have the same relative response, but in MDS just 25, they said response ratios experimentally determined to be between 0.7 and 1.8. The ratio of 0.7 and 1.8. Well, that's nearly 200% range, so it's not very precise. It sounds quite close when you talk about in ratios, but in reality, that's a 200% range, so it's not very realistic. So, in using the gradient method, they're a lot closer to the theoretical 1-to-1 than they should be. And then you get no, as I just said, no difference in recovery between the isocratic gradient and dimethylamine method. So the method is shown to be equivalent to existing methods. So in conclusion, gradient offers clear improvements. There's a little bit more work to do in terms of TDI, toluene diisocyanate, which is the other main one. But in early indications as well is that you can improve your calibration. I mentioned earlier that each monomer needs to be calibrated. There's early indications that aliphatic monomers can share calibrations because their UV signals are the same. So you wouldn't need to calibrate for like BDI and HCI, which would be a simplification. Just a few discussion points for anyone who's interested in diisocyanates. Big problem with the method is 1,2-methoxypyrazine is restricted in several countries, including the UK. You need a special license from the government to handle and transport and stuff because it comes under misuse of drugs regulations. Therefore, alternatives are always being sought. The alternative is the dimethylamine method, which is used as well in many countries. But unlike HPLC, you can only see what you're looking for. The dimethylamine method and HPLC will find anything. So it's not recommended for use in the UK. There's a diaminonaphthalene method that's been proposed, and that works a lot more. Like you react the diaminonaphthalene with the isocyanate and then measure the product of the diaminonaphthalene, which is changed but not bound to the isocyanate, rather than measuring the bound species. So it's a simplified method. But the difficulty with those is you've got to verify that only the isocyanate will do that to diaminonaphthalene. So it's a complicated a complicated method to validate, but a simple method in theory to use. If you could obtain a nitrogen-specific detector, then you could use the dimethylamine method by HPLC. And that would be very nice, but no one makes a nitrogen-specific LC detector. So, any questions? Oh, you've got most of my time, I think.
Yeah.
Sorry about that.
Are there any questions? I'm just going to ask one. Are there any implications for having a much more consistent and sensitive method of analysis for the workplace exposure limits?
Well, yes, absolutely. And the workplace exposure limit is and obviously the later peaks are broader, you have less sensitivity.
Yeah.
If your isocyanate is mainly those peaks, then you will struggle to measure it. Measure the workplace exposure limit with the isocyanate method because the sensitivity is a lot lower. those things. So increased sensitivity will allow you to reduce, to get to levels below the exposure.
Okay.
But it is a very sensitive method anyway.
Yeah. Okay. Oh, thank you,
It's
Jason.
not worth